Dear quantum folks, this is our very first chapter in this series. In this chapter, let's dive into the heart of quantum theory by exploring its axiomatic structure. But first, what exactly is a physical theory? A physical theory is a mathematical model that describes and predicts natural phenomena. It's our best attempt to understand and represent the workings of the universe. Classical physics, for instance, gave us a set of laws that work remarkably well for everyday objects. But when we peer into the microscopic world of atoms and subatomic particles, we need a different framework. That's where quantum mechanics comes in. Now, why do we need axioms in quantum mechanics? Axioms are the fundamental assumptions or starting points of a theory. They're like the rules of the game. In quantum mechanics, we need these axioms because the quantum world behaves in ways that are radically different from our everyday experience. We can't rely on our intuitions, so we need a rigorous mathematical framework to describe this bizarre quantum reality. The four fundamental axioms of quantum mechanics. Quantum mechanics is built on four fundamental axioms. The state space axiom tells us that the state of a quantum is a vector in a complex Hilbert space. Don't worry if that sounds like a mouthful. Think of it this way: in classical physics, we might describe the state of a particle by its position and momentum. In quantum mechanics, we use this mathematical object called a state vector, which contains all the information we can possibly know about the system. This state vector is the key to one of the most mind-bending features of quantum mechanics: superposition. Unlike classical systems, a quantum system can exist in multiple states simultaneously, until we measure it. It's like Schrodinger's cat, both alive and dead at the same time, until we open the box. Moving on to the observable axiom. This axiom states that every measurable physical quantity, or observable, is represented by a Hermitian operator. Now, what's a Hermitian operator? It's a special kind of mathematical operation that ensures our measurements always give us real numbers as results, just like in the real world. These operators are crucial because they connect the abstract world of state vectors to the concrete world of experimental results. The measurement axiom is where things get really interesting. It tells us what happens when we actually measure a quantum system. According to this axiom, when we measure an observable, the state of the system instantly jumps or collapses into an eigenstate of that observable. This collapse is probabilistic, and the probabilities are determined by the initial state of the system. This is the famous collapse of the wave function that caused so much debate in the early days of quantum mechanics. Finally, we have the evolution axiom. This tells us how quantum systems change over time when they're not being measured. According to this axiom, the evolution of a closed quantum system is described by a unitary transformation. In simpler terms, this means that the evolution of a quantum system is smooth and deterministic, until we measure it. It's only the act of measurement that introduces randomness into the picture. These four axioms form the bedrock of quantum theory. They give us a mathematical framework to describe the bizarre behavior of the quantum world. As we proceed through this course, we'll see how these axioms lead to the strange and powerful phenomena that make quantum computing possible.